In this video, we'll be continuing a lot of the ideas on the first two sections of Chapter 3, finding minimums and maximums. But this time we're more concerned with what are the absolute minimum and maximum values that a function attains either on an interval or throughout the entire curve. So basically, if in our function the largest value in the entire range we call the absolute maximum, where the smallest we call the absolute minimum. So taking, for example, this particular random graph of a function, we can see that it attains a minimum value. It appears to be at A, we have the smallest point on the graph, the lowest point. And then the highest point, the absolute maximum, occurs at D. And as we know from 3.1 and 3.2, we also have relative mins and maxes. Technically, all absolute mins and maxes are also considered relative maximums, which coincide with the critical values. But an idea that the extreme value theorem presents is that while a function may have mins and maxes on at the critical values, of course, sometimes it does, sometimes it doesn't, like at this location here, whereas at D, it actually has an absolute max. Whereas the critical value at B has a local maximum. And again, we can use first and second derivatives to make those determinations. But however, sometimes at the beginning or end point of the function's domain, it may also have a min or max value as well, which is sort of the point that it brings up. But basically, we could identify, like, for example, points A, B, C, and D, as the example says to do. It says to identify all local and relative extrema. So let's go ahead and label them. But, like, for example, for some reason, my thing is being a little finicky. There we go. My tablets should be working now. But like for example, at point when x is equal to D, we have an absolute maximum value. Whereas like when x was equal to A, we had an absolute min. And there should only be one point unless there's a tie value for the absolute min or maximum on a function. Some functions don't have absolute mins and maxes. Like if a function were to tend towards infinity, like any polynomial, often has an end behavior where it heads towards infinity. So polynomials don't often have absolute mins or maxes. They sometimes have one, but never both. But in the category of random functions, it could have one, it could have both, but it's a unique point. And all other mins and maxes are called relative or local. So we call this a relative maximum because, again, the idea is in the immediate vicinity, it is the highest point on the curve, ignoring the rest of the function. And we'd have a relative or local min here, again, synonyms, as well as at E, we'd have a relative min. But notice at the endpoints, that's the idea, is that you could have relative or local mins or maxes at those particular points. Let's go ahead and look at the definition. It says, suppose that f is a function with domain I. It says f of c is an absolute minimum if f of c is less than or equal to f of x for all x in I. Or all that's saying is that at the evaluation point f of c, that's always smaller than every value of x on the interval. So like looking at, for example, f of a in this case, f of a is an absolute min because it's less than literally every other value. Let's just say that's -5 or something. It's never going to go below that. So it would satisfy the definition of the absolute minimum. And same for absolute maximum. Like at D, there's never going to be a higher value of this function than at this point. So f of c is greater than or equal to all values of f of x, no matter where it is in that interval. And the extreme value theorem is kind of extending on this idea and kind of bringing up a point which I mentioned earlier, which is another important point working towards the ideas in this next section. It says a continuous function f defined over a closed interval AB must have an absolute maximum and an absolute minimum value over AB. So what I just mentioned a minute ago was that if it heads towards infinity, it may not have a minimum or maximum. But the key differentiation here is if it's on a closed interval. If we're looking at a specific fixed value, like for example, this function we're just looking at from A to E. And notice that it is continuous. It has no gaps, breaks, weirdness. And we can trace the entire curve without lifting our pencil, which is the idea of continuity. But this is, it has to have an absolute min or max. And it kind of makes sense because, you know, imagine that I'm starting, you know, here's my interval on my x-axis from A to B. If it starts over here at somewhere at A and is continuous, again, it could go up or down or however, whatever the behavior of the function looks like. If it's continuous, it has to, you know, take on values at every point in between A and B. And, you know, given its continuity, it has to have some biggest point. It has to have a smallest point. There is no weirdness to it. Now, any break in continuity can kind of ruin this idea because, let's say, for example, the function has a vertical asymptote or has like a weird gap or break or something like this. Certain functions over A and B may not have, may tend to infinity. But if it's continuous, it cannot do that. And so that's why continuity is important for the extreme value theorem to make sense. But at the end of the day, we have our, you know, it's like our max or the top of our range, and we have our min, the bottom of our range, which coincide with, again, critical values or the starting and end points if those were the highest and lowest values. And this all leads us to what's called the maximum minimum principle 1. It says, suppose f is a continuous function defined over a closed interval. To find the absolute maximum and minimum values on this interval, it says first find f prime, which obviously we need to do this to find the critical values, and that's what step B is. Determine all the critical values in a B. That is, find C, for which f prime of C is 0 or does not exist. Step C, list all the values on the interval. So it's sort of like, well, where are all our critical values? We have the start point, and also not just the critical values, but the starting and end point are, it's sort of like, what are our options for mins and maxes? The starting and ending points could be, but any critical value on the interval could also be. And basically we want to list, well, what are all those particular values in the interval? Starting at A, all the critical values in between, going all the way to B. And then what it says for step D is evaluate f of x for each of those points in those particular steps. So then it's sort of like, well, what's the value of the function at all of the critical values and at the start and end point? And all it says to do next is figure out, well, what's the largest? That's going to be your absolute max on the interval. What's the smallest? That's going to be the absolute min on the interval. Because it's continuous, meaning that it should have a defined derivative at each point. Again, assuming it doesn't have any weird cusps or something like that. But yeah, that's exactly what step D says to do, evaluate at each. The largest of what you obtain is the absolute max, and the smallest is the absolute min. Again, based on the logic for what I was saying, we're just basically finding all the special points, figuring out which one's the biggest, and there's that. So let's use the minimum maximum principle number 1. Let's test it out and try an example. So this one says, let f of x be equal to the function 2x cubed minus 6x plus 4. And it says find the absolute min max on particular interval. So if we're going to do it on various intervals, it could have a different result based on the critical values in the interval. But no matter what intervals you're looking at, you always need to start by finding ideally all the critical values, which means take the derivative, set it equal to 0. So if I take the first derivative here, we would have 6x squared minus 6. And the derivative of 4 would be 0. And now setting this equal to 0 to find the critical values, we'd have 6x squared is equal to 6. Or again, we could use factoring. Divide by 6x squared is equal to 1. Which again, there's always two solutions. 2x squared, we'd have x is equal to plus or minus 1. If I were to take a square root. But basically, we have two critical values in this interval. Let's just call them C1 is equal to -1, C2 is equal to +1. And again, if we're using the minimum maximum principle to find absolute mins and maxes, we will need to list all of the points on the particular interval. So, and also every single interval will have a slightly different process. So the first one says find the absolute min and max over the interval -3 to 0. So basically, as what it said to do was list all of the values, basically from left to right, starting with the endpoint and all critical values in between. So there's only one critical value in between -3 and 0. It's just -1 because 1 is outside of the interval. So basically, we're gonna have 3 potential options for our absolute mins and maxes on this interval, either at the endpoints or the critical values. In this case, just 1. And then if I evaluate each of those in f of x, so I would want to take, well, what is f of negative 3, what is f of negative 1, and what is f of 0, in order to solve those. So I'll just erase that, but that's kind of what I'm doing next. So now evaluating each of those things, again, plugging into the original, not the derivative, we would get, so I guess we'll start with 0 because that's really easy. Plugging in 0, 0, 0, 4. So that would be 0. We're not really sure. We need to find them all before we can determine which is the min and max. If we plug in negative 3, this would give me negative 3 cubed is negative 27. So negative 54, then it'd be plus 18. Let's just go ahead and use a calculator to do this. 2 times negative 3 cubed. So I don't make a mistake and have to redo the whole video. Plus 4. And that would leave me with negative 32. And then if I check what is so these are the critical values, and then these would be f of the critical value. We'll try to organize my work a little bit better. And then if I were to plug in negative 1 instead, let's just go ahead and change what I'm plugging into f. This would give me 8. And again, once we've found all the values, basically the largest that you obtain, which is obviously 8 is the biggest value that I've attained, this point would be my absolute maximum. So the absolute max here is negative 1 comma 8. And now, again, a lot of times we like to write our points as ordered pairs on the curve, like coordinate. I don't know why this yellow is kind of ugly, but it is what it is. And then the smallest value obtained, which is negative 32, will be the absolute minimum. Sorry, I forgot to write maximum. The absolute minimum value on the interval will be negative 3 comma negative 32. So yeah, and this one was the absolute maximum. And 0 comma 0 was basically it's kind of like this was the critical value in the middle, which turns out to be the absolute maximum. This was the left part of the endpoint. And another thing that you can do here is if you just graph your function on this particular aspect of the domain, you should be able to see it and kind of imagine what's happening. So let's go ahead and do that. Our function is 2x cubed minus 6x plus 4, and we can go ahead and put it in the graph. Now again, if we graph it, we're going to see the whole thing, but this is not what we're concerned about. We're concerned about a more specific interval when x goes from negative 3 to 0. And if I adjust my interval, notice I can't quite see what's happening to the left, but I know that the absolute minimum value is negative 32, so it would make sense to graph it from the minimum value, let's just say negative 35, to 10 to encompass the full range of the function, which is from negative 32 all the way up until 8. And what I can see here is that at negative 3, I have my minimum value. You know, again, we could always create a sketch to imagine what's going on in the given interval. But from negative 3, it's kind of going up like this and coming back down. And, oops, that's not exactly correct. More like that. But again, at negative 3, we have our absolute minimum, and at negative 1, we had our absolute maximum. And the graph coincides with our findings. But again, we don't need to graph it if we're using the extreme value theorem, because we know critical values are either going to, or minimums or maximums are either going to happen at the critical values or the endpoint. So if we just test them all, figure out the answer, we don't have to do any other work beyond this for finding the absolutes. So let's do this also for the other intervals in example number 2 from the packet. So if we were doing this from 0 to 3, it would be slightly different because negative 1 is not a critical value on the interval. Again, we always start with the and this is not just CVs, this is also CVs and the endpoints. But if we're doing a C critical value 1, etc., basically in our list of our critical values and our endpoints, we'd always start with 0, and then the only critical value in this interval is positive 1. So 0, 1, 3, which is the other endpoint. And again, we'd want to check what is f of c, what is the evaluation of the function on that particular interval. Well, we already know f of 0 is 0. F of 1 is going to just be 2 minus 6, negative 4 plus 4 is also 0. Let me do that again. 2 minus 6, yeah. And then for 3, we will get 2 times 3 to the third power. Well, we already have this in our calculator from last time. But we could check what happens at 3 as well. Let's change this up. And this would give us 40. And basically, again, our absolute max on this interval will be the largest value, 40. Absolute max is going to be 3, 40. That particular coordinate. And the absolute min is a tie. And sometimes you could have a tie, and we can go back and see, well, what happens if there is a tie? It doesn't specifically say. So what you could say is there's a tie for 2 points being the absolute min or max. But if you have the condition that only one is allowed to be absolute, you might say, okay, there is no absolute due to the tie. But here I'd say, well, both are the absolute minimum values of the function on the interval. And again, we could adjust our window for our graph from, let's just say, -5 to 50 to see what's happening on the interval when x goes from 0 to 3. And this, will take on a different part of the curve, but what we can see, is that 0 is not 0. What am I talking about? So I messed this up earlier. Luckily, I don't think it mattered. 0 should give me 4, not 0. Whoops. But yeah, thankfully that was neither the absolute min or maximum. You probably were wondering that as I was doing the math. But this will clear up all of our problems. But it's worth thinking about what happens if you do get a tie, so that you know how to distinguish it. But anyways, in this particular case, it appears the critical value of 1 is the absolute minimum value, because that's the smallest output. And again, this is now more... Now, again, using a calculator, you can check these things out. I can see I've got my absolute min on this interval, and the absolute max is over there. But again, you don't have to use a calculator if you're using the extreme value theorem and the min-max principle number 1. Now, if there's more than one critical value, it's just extending the same idea. Let's say we were doing this on the interval -2 to 2. Then we're just kind of putting them... We need to make sure to put all the critical values in between. So from -2 to 2, we had 2 critical values in this interval from -1 to 1. And then we would want to evaluate our function at those, the endpoints and the critical values in between. Now, we already know that -1 produces 8. And we know that 1 produces 0 because we checked those. But we have not yet checked 2 and -2. So 2 on this curve, let's just use the graph because we already have it. 2 would actually produce 8. And -2, let me go back to the main screen. And let's just swap this up to -2 so I can check what f of -2 is. F of -2 appears to be 0. But again, in this case, notice that we have some ties, and basically we just have more things to check, more options for absolute min and max. There's still only one unless there's a tie. Like in this case, we'd say these are tied for the absolute min and max. These are tied for the absolute min. And in the next video, we will talk about the principle number 2. Very similar ideas for finding absolute mins and maxes.